Last big concept of calculus. Congratulations. Well, calculus 1 at least. Okay, so we're going to be talking about one of my favorite subjects is the volume of solids as we rotate them about different things. So this is really cool to me. The reason being is what we are going to be doing, that's not what I wanted, is say that I have this figure, something like that. All right, so it kind of looks like a half of a violin or something. But if I want to make a fancy vase, what I can do is I can rotate this figure about an axis. Say I rotate it about the x-axis, and what it does is it maps that figure in a 3D space around the x-axis. So if you can imagine this, it comes up out of the page, and it also, like in all directions, that figure fills in the space. So let me go to that app again, and we're going to do the disk method first. I want to have, let's see, what's a fun one? How about sine of x? Where's my x? Where is it? Where'd it go? Come on! X squared. Sure. Why not? All right. That's funky. That's cool. Okay. They can't give us enough disks. I can only make there be 200. There's not enough because really there's going to be infinitely many. But let me make my area smaller. So let's say I just talk about this region right there. So if I am taking that region, where'd it go? It's so dark. Why is it so dark? It's annoying. I'm going to zoom in. There it is. Okay. So I don't know what I made, but it is this figure. So it's taking this region right here, this, I don't know, it looks like half of something, and it's rotating it about the x-axis. If I change the line that I'm rotating it about, say I move my line up here, it's taking the shaded region and rotating it about the line y equals 1 now. So it makes a different figure. So that's cool. I think they use this some for computer simulations of things, some in, I'm sure, engineering for definites. But depending on what we rotate it about, I wonder if they'll let me do the line y equals x. No, they're not letting me do it. They're only doing y equals. I wonder if you're not going to do the shell method. But this would be something that it looks like if I rotate this about the x-axis, or sorry, the y-axis, where it would take this region right there and it's rotating it about this line to make kind of an open figure in there. Again, they don't show as many intervals as I would like, but hopefully this gives you somewhat of an idea of what that could look like. So it's kind of cool with everything that we can do with this stuff. All right, so how do we actually do that? Well, first way is called the disk method. The disk method is just like if I have a disk, right? So if I talk about the disk, I have a disk of some height, and I'm going to add them together. So the volume of this disk is really just a cylinder, so it would be pi r squared times the height, right? That is the area of my figure. So now what we are really doing is we have that disk and we are rotating on its side. It's building disks that are standing straight up and down. So in order to do this stuff, I need to figure out what is my radius, and my height is actually going to be my integral. So it's going to take the sum of all those little infinitely small, but really they have size, disks, and they're adding them together. So if I were to say that this is going from A to B, my area of this solid would be pi from a to b, my radius squared, which would be whatever my function is squared, times the height, and the height is my integral. That would be the area of this region. So that is essentially just your disk method in a nutshell. And again, if you don't understand the radius, it's just like we were doing on the cross sections. The radius is that height right there, such that when it rotates it around, right, you double that radius to get this entire length right there. So the radius in this case is just the function. The radius is some things, is one of the harder things to make sure that you really have a good grasp of. So if you can figure out the radius, these usually aren't that bad. So the biggest deal is just figuring out what is my radius. So let's get into one. Find the volume of a solid created by revolving the square root of sine of x about the x-axis on the interval from 0 to pi. So let's see, the square root of sine of x would look something like that. Actually kind of looks like sine of x. From 0 to pi. Yep, that should be right. So it's taking this region and it's rotating it about the x-axis. I like to put this little notation. You don't have to do this, but I like to do that just to remind myself where I am rotating it about. Because you'll see in the next one, we're going to rotate it about the line y equals 1, so it's going to change as far as where we are rotating. So this helps me in order to figure out the radius. The radius is this unit right there, so my radius is just f of x. If it helps you to notate that as well, notate that. On the x-axis from 0 to pi, so my volume would be pi, the integral from 0 to pi of my function squared, so square root of sine of x squared dx, and that would be it. That would be your volume. So this is setting up but not evaluating. If you wanted to evaluate, you could do that, right? That would just be sine of x dx. So this would be what? Pi times negative cosine from 0 to pi, which would be pi times 2, right? Negative 1 plus 1. Yeah, negative 1 plus 1. Yeah, so that would be 2 pi. That would be the volume of my solid, units cubed. So that would be one that you would actually be able to find the volume. Maybe you could use calculator, but a lot of the times on these things, if you have this, mostly what I will see on the AP test is it's either with a calculator or they will ask you to set up but do not evaluate. So you're going to get a lot of set up but do not evaluate on the test. So when I say set up, do not evaluate, that is your setup, do not evaluate. That's mainly what we're going to be doing today in notes as well. Because by this point, all the integration techniques are the same. Until you get to BC, you're not going to learn any new integration techniques. First one you will get to do is integration by parts. All right. Find the volume of the solid bound by 2 minus x squared, y equals 1, about the line, y equals 1. So let's see. If I think about my function, 2 minus x squared looks something like that. Y equals 1 looks something like that. So I'm talking about this region right there, and I'm rotating it about my line y equals 1. So thing is I need to think about the radius again. The radius, like I said, it's going to be some of the hardest things because the radius here is this measurement. So I can't just use straight up f of x, because if I use straight up f of x, it'll be too much, right? F of x is this part right here. So what I need to do is it's really just the height but minus 1. So my radius in this case would be f of x minus 1, because I got to get rid of, oh, that's way too big. I got to get rid of that height right there, right? Because this is the radius. Ooh, I don't like that. The radius. how did I want to do this? Yeah, the radius plus 1 is f of x. So the radius is f of x minus 1. Right, so the radius plus 1 is f of x, is how I was kind of coming up with that. If that helps you to write an equation, you're more than welcome to do that. Okay, so once I have the radius figured out, that's really the biggest part about this thing. So I'm going to go from the intersection of these two things. So I need to figure out what the intersection is. So I need to figure out when 2 minus x squared equals 1. Well, that would be, it looks like x would be plus or minus 1. So I have it from negative 1 to 1, pi times the radius squared, which was f of x minus 1 dx. And another thing you can do too is, since 2 minus x squared has y-axis symmetry, it is an even function, is you can find the volume of your right part and double it in order to get the volume altogether. So that would look like 2 pi 0 to 1 of the same radius. That would look like that. And the nice thing about that, the reason I would do that would be in order to be able to do the integral in terms of 0, because then you would have minus f of 0, so that would just be whatever it is, right? It's much easier to use 0 than it is to use negative 1 and 1. I believe Mr. Osborne is also a fan of that, if you guys have him next semester. Okay, but this would be your setup, but do not evaluate. Either one of these would be correct. All right. Find the volume of the solid bounded by this function, y equals 4, y equals 1, and x equals 0 about the y-axis. Let's see, let's draw our graph. And if I think about this, this is negative y plus minus 4. So I'm going to have an intercept at 0 and an intercept at 1, 2, 3, 4. And it is a negative y squared. So I should have a negative parabola going, that's a pretty ugly parabola, but it should be a graph something like that. And notice this is a function in terms of y. So that's how I will treat this, especially since they're talking about the region bound by y equals 4, y equals 1, and the x-axis. So it's talking about this region right there around the y-axis. So my radius here is just the function right? So it's just going that distance from the y-axis. That's that function. That's how you get those heights there. So I have the volume would be pi integral from, it tells me from 1 to 4, 1, 4, radius squared, so negative y squared plus 4y squared, and then make sure you're integrating in terms of y. All right, give me just 1 second. All right, next we're going to be getting into the washer method. So not a dishwasher, but a washer is, if you don't know, essentially a ring with another circle inside, different sizes. Move that. But such that all this area would be like metal or plastic or something like that, but you could put a screw through it such that the screw holds the thing together better. It just gives essentially the screw more surface area. But moral of the story, the washer method will be like if I'm looking at it from the side, similar to our disk method, except there are going to be 2 radii. So what you're going to have happen here is you will have a graph something like, say I look at x squared and the square root of x. And I want to take this region and I want to rotate it about the x-axis. So if I want to do that, And if I rotate this about the x-axis, I'm going to go back to this. Washer method. I don't know which functions I have here. I think that's linear. Let's see. X squared. Okay. All right. So I'm only doing it of that first intersection point. You could continue on if you wanted to and get some crazy looking shape. I don't even know what's happening really. That looks wild. Yeah, I don't know. That's interesting. But I'm only talking about this region in here where they intersect. So if I zoom in on that, notice there's a part missing there. It's not a bunch of discs, it's a bunch of kind of rings or washers that have been added together. So I need to be able to think about how I can take that piece out. And the way that I can do that is with the washer method, because essentially what is happening here is there is a radius, a small radius, that I have taken out the volume of, and there is a big radius that represents the overall distance to the outside. So with this one, we're going to kind of need to think about both radii here. And in order to do this, I think about what I call the big R and the little r. In this case, the big radius is what? Square root of x. And the little radius is x squared. And in order to figure out the volume, it's like I need to do both of those washers, but take out the washer of the little radius. So the volume here would be pi r squared, big R first, r squared height minus pi little r squared height, such that it does the volume of the big part using the washer method, or the disk method, and then it takes out the volume of the little part using the disk method as well. So it's just two disk methods getting us to the washer method. But I can factor out the pi and the h to get to r squared minus r squared. And how this would look with an integral would be pi times the integral from a to b or whatever, big R squared minus little r squared, dx or d, whatever we're integrating in terms of. So this essentially right here off to the side is your washer method, where we are taking out the smaller radius. So again, it's going to be really important to take note of where your radii are. What's the big radius, what's the little radius, so I'll always try to do that for you guys as well. Okay, find the volume of the solid created by rotating the cross-section created by these equations about the x-axis. So I have y equals 2, and up 4, and then a parabola. So a parabola that's pointed downwards. So my region is this cross-section right here, and I'm rotating it about the x-axis. I'm rotating it about this. So I will have a region in here that I will have a blank space. So for this problem, my big radius would be the function of 4 minus x squared over 4. So big R is 4 minus x squared over 4. Little r is just 2. And then I'm going to need to find their intersection point in order to be able to find what my limits of integration are from a to b. So let's set those equal to each other. I'm going to multiply by 4 first to get 16 minus x squared equals 8. Move over your 16, so x squared equals 8. So x equals plus or minus root 8. You can leave it like that. You can make it 2 root 2 if you want to as well, but it really doesn't matter. Okay, so my volume would be, if I were to set this up, pi from negative root 8 to positive root 8 of 4 minus x squared over 4 squared. So that's big R squared minus little r squared, which would just be 4. And I'm doing it in terms of x on this one. And that would be it. That would find your volume of that figure. I don't know, it kind of looked like a donut with like a flat center or something. Okay. All right. last one we're going to be getting into, because really a lot of this stuff is just the same thing over and over and over. So let's see. The volume of the solid by rotating root x, y equals 0, and x equals 3. So I'm going to draw it off to the side here. So y equals root x equals 3, and y equals 0 is just that line, so I'm talking about this region right here. So nice thing is if I am rotating it about the x-axis, that's just the washer method. There's no hole or anything in the center. Because I'm doing it, I can duplicate. Yeah, duplicate. Okay, so if I'm doing it about the x-axis, then this whole part in here, this is all filled in. So that's going to all be a filled in figure all the way around. So I'm just going to use the disk method. So my volume is pi, the integral from 0 to 3, because that's where it's being cut off, of my function in terms of x. All right, now if I do it by the y-axis, here, okay. Now I'm doing it by the y-axis. So if I'm doing it about the y-axis, what I will want to do is write this equation in terms of y. So this would be x equals y squared, which if I take the whole thing, it would be a parabola something like that. So I'm just not using the negative part over there. But the important thing here is to realize, what is the big radius? Well, the big radius is x equals 3. And the little radius is my function height. All right, so the little radius then would be y squared. So with this thing, I would have the integral, so pi from 0 to, let's see, if x is 3, then y would be root 3 of big radius squared, so this would be 9 minus y squared squared, all in terms of y. All right, line y equals -2. So I'm going below the x-axis on this one, right? I'm rotating it about y equals -2 down here. So my big radius would be the function value plus 2 units, because that radius is adding 2 units down there. So the big radius is square root x plus 2. The little radius is this height right here, which is just 2 units. It won't even matter, like if your question is, do I take it as -2? It won't really matter because we're going to square it anyways. So you can do that if you want to, but it's going to be squared, so it'll end up being positive. So I have pi from 0 to 3 of root x plus 2 squared minus 2 squared dx. Okay. All right, the line x equals 6. These are always the most challenging to me because our big radius is this distance right here. So if that's the big radius, I can't just say it's the function value in terms of y. All right, now I'll need to do it in terms of y because I'm rotating it kind of about the y-axis type deal. So I will treat this as y squared, but if I just do y squared plus 3 or something, that's not going to come out. Because y squared plus 3, well, y squared right here, and then if I add 3, it won't really get me there. But notice, this is y squared, so my big radius, really, 6 is equal to my big radius plus y squared. Right, because 6 is my entire distance away, and that is y squared plus my big radius. So the big radius then is y squared minus 6. No, did that totally wrong. What's wrong with you? Big radius is 6 minus y squared. Yeah. All right, and the little radius, that's all just 3 units away, so the little radius would just be 3 there. So if I'm writing this, I have pi. I already determined that that's 0 to root 3. The volume equals this, from 0 to 3, of the big radius squared, so 6 minus y squared squared, minus the little radius squared, which would be 3 squared, and I'm doing it in terms of y this time. Okay, and that's it. So again, the hardest thing is just to set these things up. But get some practice on it. Once you set them up, they're not super difficult to integrate. Most of them are usually pretty easy. That one would be kind of a pain, but my guess is we would not make you do that. Well, not my guess. I'm not going to make you do that. I don't think the AP test does either. But if you can get the methods down and setting them up, they are not so horrible. Okay, congratulations. After this, we're going to do an AP packet practice to get you guys some more practice on the volume stuff. But please let me know if you have any questions, and I will talk to you all soon. Bye.